All right, segment 5. So we've been talking about types of questions, and I've just introduced you to the mole. So if you remember, the mole is 1 mole is equal to 6.02 times 10 to the 23rd particles, and our particles can be molecules, formula units, or atoms. So how many molecules of CO2 are there and 4.56 moles of CO2? All right, so how many molecules of CO2 are in 4.56 moles? So we're going to start with 4.56 moles CO2. And so I've subscript the CO2 here for the moles. I do that simply because when we move to harder questions, there might be several different compounds in there. And so you kind of want to keep track by saying, not only do I have moles, but I have moles of CO2. Now what I want to do is cancel out those moles of CO2. Now I know that Avogadro's number says for every 1 mole of CO2, we're going to have 6.02 times 10 to the 23rd particles. In this case, can I use molecules? And yes, I can. So this is going to be molecules of CO2. And now I'm going to turn to my handy dandy calculator. And so I'm going to take 4.56 times 6.02. That's going to give me 27.45. And of course, I'm going to bring that 10 to the 23rd out. So this would be times 10 to the 23rd. Now I'm just going to clean this up a little bit. Remember, we are going to move the decimal point over here. We need to be in scientific notation. And so we're going to have 2.745 times 10. And now since I moved that decimal point over 1 time, 23 is going to go up, right? We made a big number small. So my exponent has to go up to account for that. And so this is going to be 10 to the 24th. And then the last thing I need to do is look at sig figs. Here we have 3 significant figures. Avogadro's number is going to be a constant, but it actually does go out further. So it's 6.022. But so that one's also going to be 3 sig figs. And so my final answer then is going to be 2.75 times 10 to the 24th molecules of CO2. And so that would be my final answer. All right, good work, good work. How about the next one? We have how many moles of water is 5.87 times 10 to the 22 molecules? So here, we're going to attack it sort of the same way. We're going to start with that 5.87 times 10 to the 22 molecules of water. I'm going to make my parentheses. And this time, I want to get rid of molecules, right? So I'm going to put Avogadro's number in the bottom. 6.02 times 10 to the 23rd molecules of water. For every 1 mole of water. All right. And so now what I'm going to do is I'm going to divide and conquer that. So what I mean by that is I'm going to take 5.87. I'm going to divide that by 6.02. That's going to give me 0 0.9750 times 10. And now I'm going to apply my exponent rules. So exponent rules say that if I take 10 to the 22 and I divide by 10 to the 23, it would be the same thing as saying 10 to the 22 minus 23, and that's going to give me a negative 1 moles. Now I can't leave it this way. I have two options. I can expand it by getting rid of that exponent, or I can put this in scientific notation and change the exponent. Since it's a negative 1, I'm going to go ahead and just push that decimal out that way and get rid of the exponent altogether. So I'm going to 0.097, and then again, how many sig figs do I get? I've got 3 here, 3 there, so I'm going to keep the 5. 0 does nothing to it, and that's going to be moles of water, H2O. All right, and that's our final answer. So if you have questions about those and you've watched it a couple times and you just can't seem to understand where I'm getting things from, then be sure to contact me, schedule an appointment, or come to one of my open student hours. All right? Okay. How many atoms of carbon are there in 1.23 moles of glucose? So how many atoms? So again, we'll start with that mole. We were told it's 1.23. Oh, let's erase that. It's not looking good. Let's try that again. Ah. All right, so we're going to start with 1.23 mole. And I'm simply going to put GL for glucose. I want to get rid of moles. My connection to moles is going to be particles. However, this is a molecule, and I'm looking for atoms. So I'm going to get rid of moles by saying 1 mole over 6.02 times 10 to the 23rd molecules of glucose. And then I'm going to have a second bracket. And for every 1 molecule of glucose, we're going to get 6, right? Because if I look at the molecular formula, it's C6, and I'm looking for atoms of carbon. So that's going to be 6 atoms of carbon. So now I can run that through the calculator. I'll take 1.23 times 6.02 times 6, and that gives me 44.4 times 10 to the 23. And once again, we can't leave it that way. So I'm going to put that in scientific notation. I get 3 sig figs again. So I'm going to keep all of those 4s. 4.44 times 10 to the 24 now, because again, we made a big number small. And then of course, that's going to be atoms of carbon. All right. Hopefully you're able to follow along with that. And again, you can always rewind, check it out again, and then see if you can figure it out. If you're still struggling, don't hesitate. Get a hold of myself, schedule an appointment, come to a student hour, or get tutoring, one of the two. All right, our last question of this type. How many moles is 7.78 times 10 to the 24 formula units of magnesium chloride? So we're going to take 7.78 times 10 to the 24th. So formula units. My program's being very laggy here, so I apologize if this is kind of breaking up as I'm writing. So 7.78 times 10 to the 24th, this would be formula units, and I want to get into moles, so I'm going to put 1 mole on top. We're going to put Avogadro's number on the bottom. And I'm going to take 7.78, I'm going to divide that by 6.02, 7.78 divided by 6.02, and I get 1.293 sig figs times 10 . And again, I'm going to use my exponent rules. 24 minus 23 will be 10 to the 1. And again, since it's a 1, I'm going to go ahead and expand that. And so my final answer is going to be 12. Doesn't look like a 2, does it? There we go. How about that? 12.9 moles. And again, we could subscript this magnesium chloride if we'd like. All right. Hopefully you're getting the hang of that. And you're going to be able to measure some moles. So that's if we're going from moles to particles and particles to moles. Next thing we're going to look at is measuring mass. So hopefully, you kind of remember we're talking about atomic mass and we used AMUs. And I told you, don't worry about AMUs because later on I'm going to change that unit. And here it comes. So here's that change. The decimal number on the periodic table is also the mass of 1 mole of these atoms in grams. So I don't want to call it AMUs anymore. I want to relate it to mass, to real mass, grams. And so we call that gram atomic mass. What that means is the mass of 1 mole of an element in grams is what we're going to find on the periodic table. So in other words, if I look at the mass of, say, carbon is 12.01 grams per mole, right, according to the periodic table, because the mass, the atomic mass, is 12.01. Now that's saying that if I have 1 mole, 6.02 times 10 to the 23rd atoms of carbon, it's going to weigh 12.01 grams. If I have 6.02 times 10 to the 23rd atoms of hydrogen, it's going to weigh 1.008 grams. And we can do the same game for iron using the periodic table. Again, it would be 55.85 grams. This is going to allow us to make statements of equality, right? That means we can say that there are 12.01 grams of carbon equal to 1 mole. And again, 1 mole of carbon, right? Of carbon. Now, what that's going to allow us to do is count things by weighing them. I don't know if you've thought about it or not, but counting up to the mole would take forever. I mean, we don't really spend a lot of time talking about the size of that number, but let's think about it. If you had 1 mole of pennies, you could distribute that amongst your entire family, even your third and fourth cousins, and each one of you would be able to pay off the debt for the nation, the trillions of dollars of debt. So keep in mind how big a mole is. It's a huge, huge mole. It's a sextillion. All right, it's in the sextillions, 602 sextillion. Huge, right? So you have millions, billions, trillions, quadrillions, quintillions, sextillions, right? Huge. All right. We don't want to count all of those, so we want to be able to get that number simply by weighing. So we'll be able to tackle questions like this. How much would 2.34 moles of carbon weigh? All right, so we're going to start the same way. We're going to have 2.34. Oh, that's really laggy. I'm sorry. Moles of carbon. How much would it weigh? Well, now, rather than using Avogadro's number, I'm going to use the periodic table. I still want to get rid of moles. So I'm going to put 1 mole of carbon on the bottom. Except now I'm going to go to my handy dandy periodic table, and it tells me carbon is 12.01. All right. So we're going to take 2.34 times 12.01, and that should weigh, with 3 sig figs, 28.1 gram. All right. Let's see if I can try using the program in PowerPoint, see if that works out better here. It's not letting me pull the pen up for PowerPoint though. All right, well, how many moles of magnesium and 24.31 grams of magnesium? And so again, we'll set it up using the number they've given us. So we have 24 point 3.1 grams. We're going to set up our parentheses. This time we want to be in moles, so I'm going to put 1 mole of magnesium on top. And I'm going to go to my periodic table, and it turns out that this happens to be 24. This is very frustrating, it's so laggy. 31 grams. So we might think this is going to cancel out to just be 1, but remember this is a measurement. And because it's a measurement, we have to concern ourselves with sig figs. So here we have 4 sig figs, and so our final answer is going to be 1.0000 mole. All right. Almost finished this slide set, I think. So we're going to try to press through, even like I said, it's very laggy. The program I use is web-based, and so obviously my internet is starting to struggle a little bit here. Let's see. 2 more questions left. We have how many atoms of lithium in 1 gram of lithium? And so here we're going to have 2 steps. Now, if you haven't done so already, you might want to check out the folder towards the bottom in D2L under content. down there, there's a folder called Student Resources, and in there I've placed some documents, and one of the documents is a mole calculations chart. So typically I can ask you to do these calculations, and individually it's fine. You can do them as we work through them. But then when you're by yourself, it starts to get confusing about what to do and when to do it. And the mole calculations chart will help you with that. So it's simply a flow chart that puts moles in the middle and then shows you what to do to calculate particles, shows you what to do to calculate mass. Later chapters, we're going to see how to calculate a volume for a solution or how to calculate some pressures or volumes for a gas. So it's a four-piece, it's like a cross where the top is going to be the particle, the bottom is the mass, and then we'll slowly work on the solutions and the gases, which are the other two sides. Okay. So here in this question, I point this out because it's going to ask you to go from the top to the bottom and the bottom to the top of that chart. So here we want to know how many atoms are in the mass of 1 gram. So we're going to start with 1 gram, but we can't go direct, right? The only way to get, oh, this is just really laggy. I'm so sorry. We're going to start with that 1 gram, and the only way to get to atoms is to go through the mole. So we're going to start with the 1 gram of lithium. We're first going to convert that to moles, and then we're going to convert those moles into atoms. So first we'll do moles, so we'll put 1 mole on top. I'm going to go to my handy dandy periodic table and look up the mass for lithium. And according to what I'm using, lithium is 6.941 grams. And that's going to get me to moles of lithium. Now I don't want moles of lithium, I want atoms of lithium. So for every 1 mole of lithium, it's going to be 6.02 times 10 to the 23rd. Atoms. Now I run that through my calculator. So I'm going to take 1 divided by 6.941, multiply that by 6.02, and I get 0.867 times 10 to the 23rd. And again, I can't leave it this way. I'm going to have to use scientific notation for this. So I'm going to move this decimal point back. Since I made a small number big, my exponent has to go down. And so this is going to be 8 point 6.7 times 10 to the 22. And of course, at this point now, we'll be in atoms. All right. So again, I'm sorry it's so slow. That maybe that's helping. Maybe you appreciate it being a little bit slower. But the lag as I'm trying to write these problems out is really slowing it down. So hopefully it's not too bad. Hopefully you're making sense of this. Um, Again, if you're having problems with it, make sure you get a hold of me. Contact me as soon as you can, and I'll be happy to sit down with you and work through some of these problems. All right, I've got one last problem for us in this segment, and then we'll take a break. How much would 3.45 times 10 to the 22 atoms of uranium weigh? All right, so 3.45 times 10 to the 22 atoms, how much would that weigh? So we're going to start at the top of that flow chart and work our way down. So it's going to be two steps again. We're going to start with the 3.45. All right, I'm going to try. I tried to fix my internet. Let's see if it worked. So we have 5. No, still laggy as all get out. Oh, I think it actually might be worse. Times 10 to 22. Ugh, that's just horrible. Atoms. I'm just going to leave it as A, but that's atoms. Just the least I have to write, the least frustrated I get. I want to put this in 2 steps again. Again, you can do each one of these steps individually. So we're going to have 3.45 times 10 to the 22 atoms of uranium. We're going to get that into moles first. So for every 1 mole of uranium, it's going to be 6.02 times 10 to the 23. And that would be atoms. And then over here, we're going to have 1 mole. Since we're looking for a mass, the moles will cancel out. And now we're going to go to our handy dandy periodic table. We're going to find uranium. Uranium is number 92 and has a mass of 238. Point 0.03. And this, of course, will be in grams. All right. So again, pull out the calculator. We have 3.45 divided by 6.02 times 238.03. That gives me 130. Oh my goodness. And 36.4. Now I only get 3 sig figs, so I really don't need the 4. That'd be it right there. Remember, I left my exponents out because I divide and conquer. So this is going to be times 10 And here I'm going to take 22 minus 23. So that's going to be negative 1. Now I can't leave it that way. I want to fix it, put it in scientific notation. So I'm going to move that decimal point over. And I'm just going to collapse that scientific notation. So this is going to equal 13.6 grams. All right, so how much would 3.45 times 10 to the 22 atoms of uranium weigh? Well, we're going to take 3.45 times 10 to the 22, divide by Avogadro's number, and then multiply it by the molar mass, right? The gram formula mass. And that's going to give us 13.6 grams. All right, so we've done a lot of calculations today. It was a pretty long segment, a lot of it due to the delay on my end. So the next thing we're going to look at, let's see, let's turn this off, is what about compounds? So everything we've done so far has been for atoms. How will these things apply to compounds? And so that's going to be our next segment. So stay tuned. I'll probably take a break and see if I can't get my internet to cooperate with me so I can make these videos. But next we will tackle compounds and using formula masses. All right, stay tuned.